right. Thank you very much for the invitation. I'll talk about two conjectures which indeed, spoiler alert, turned out to be false. It's based on two recent papers, one joined with Irvin Hentzel from Iowa, and so I'll start. So the plan is as follows. I'll quickly remind you what the protagonists, the alternative algebras and Jordan algebras are. I will explain what the conjectures are, tell you about some experimental data which ultimately led to a refutation of the conjectures, but also contains some unexpected phenomena that still might be true, and well, conclude with a few open questions. Alternative algebras are, both alternative and Jordan algebras are some classes of non-associative algebras that were studied in studied since about 100 years ago. An alternative algebra, it's an algebra which is non-associative, but somehow the associator AB times C minus A times BC possesses some properties. It's completely antisymmetric in A, B, and C, so it alternates in A, B, and C, hence the name alternative. And the most famous example of an alternative algebra is given by the octonions of Cayley, and that was kind of one of the motivating reasons to study this class of algebras, which started by Zorn in 31.
Zorn?
Yes. Well, yeah.
I think German.
Yeah, but I mean, we say Jacobi, not Jacobi.
Jordan is Jordan,
yeah.
German. Famous Hitler.
Well, yes, so in any case, yeah, so yes, in particular with the next term, some people, many people say Jordan algebras, some people say, English-speaking people say Jordan algebras, but in any case, these are non-associative and commutative algebras in which multiplications by any element A commutes with multiplication by A square. So A square times AX is equal to A times A square X. And the motivation for Jordan came from quantum mechanics. He observed that Hermitian matrices, which are important from the quantum mechanical point of view, are not closed under product, but if you consider the symmetrized product, then you get from two Hermitian matrices another Hermitian matrix. And so he said, for that reason, it's maybe important to study this structure. Eventually, it turned out that this operation in an associative algebra satisfies some surprising properties not following from this defining property, but that's another story. For everything today, the algebras will be over a field of characteristic zero. For example, you can think about algebras over rational numbers. It's and unlike free commutative associative algebras, free associative algebras, free Lie algebras, free alternative and free Jordan algebras are not really well understood. So there are only some very partial results, incomplete results that we know. So if we take one generator, then the story is not terribly interesting. Both the free alternative algebra in one generator and the free Jordan algebra in one generator is just the algebra of polynomials. So there is no room for any non-associativity. Emil Artin proved that the free alternative algebra in two generators is the same as the free associative algebra in two generators. So for two generators, there is still no room for non-associativity. Things come in later on. And Kohn and Sheshov proved two results from which altogether it follows that the free Jordan algebra in two generators is the, you take the free associative algebra in two generators, it has an involution that reverses the order of factors, and the fixed points of this involution with the product 1/2 AB plus BA is going to be the free Jordan algebra in two generators. Then somehow for three generators, for the alternative algebra, in three alternative algebra in three generators, there is a known basis, which is already very complicated. So it was obtained by Iltikov in '84. It's an insanely difficult technical paper, and but at least we know something. For free Jordan algebra in three generators, we don't really know how to describe it. And somehow, if the number of generators gets large, then these free algebras start exhibiting absolutely bizarre behavior. So there are nilpotent elements, zero divisors, something that you don't expect from free algebras at all. So it's so, for example, there is a result that says that if you take the free Jordan algebra on at least 28 generators, then it contains nilpotent elements. Voila. So it's a big mystery. And then again, people who study non-associative algebras think that these two types of algebras are among the most interesting ones, so they want to understand at least something about it. But not much is known, so yeah. And the conjectures I'm going to talk about were conjectures that somehow, if they were true, they would give a lot of new information about free Jordan algebras and free alternative algebras. So let me remind you, or tell you if you never heard of this story, about the wonderful construction that relates Jordan algebras with Lie algebras. So it's nowadays it's called the Tits-Kantor-Koecher construction. So originally it goes back to a paper of Jacques Tits, which then was generalized slightly by Kantor and Koecher. It's all in the 60s. So let's take a Jordan algebra and let's consider the commutator of the two left multiplications by A and by B. Let's denote it DAB. From the definition of Jordan algebras, it is possible to prove that this DAB is always a derivation of the Jordan product. So DAB, it is of C. It's the commutator, so it's A, B, C minus B, A, C, the commutator of the multiplications. Yet it is known that DAB of CD is DAB of CD plus C DAB of D, etc., for any A and B. And so people who study Jordan algebras call these derivations inner. Well, they are constructed as some internally in terms of the algebra structure. And so the construction of Tits-Kantor and Koecher goes as follows. You take the Jordan algebra J, you consider matrices with trace 0 with coefficients in J, SL2 tensor J. If J were associative commutative algebra, then this already would be a Lie algebra, some sort of current algebra construction. But since J is non-associative, SL2 tensor J is not going to be a Lie algebra, the Jacobi identity is not satisfied. But if you add the space of inner derivations, turns out that you can make this close into a Lie algebra. So you say that the bracket of X tensor A, Y tensor B from SL2 tensor J is the bracket of XY tensor AB plus some, well, the killing form SL2 times DAB.
Question about inner derivations. Can one consider symbols DAB also form Lie algebra?
Yes, they form a Lie algebra. This is the third. They are closed. Yes, inner derivations form a Lie subalgebra of the Lie algebra of derivations.
So it's like the base square of...
that will be on the next slide, 1 second. So this is a construction. So D of AB acts using the fact that it's a derivation and the bracket of two inner derivations, it's an inner derivation. And after some effort, you can prove that this satisfies the Jacobi identity. Now we're talking about free algebras. Free algebras is something categorical, functorial, and inner derivations in general are not a functor. So somehow this Tits-Kantor-Koecher construction for studying free Jordan algebras doesn't seem...
Functor, not natural. No,
they're not functorial. Like,
but derivation is also not functorial.
That's correct. That's correct. But this construction uses inner derivations, and inner derivations certainly are not functorial, right?
What do you mean? No, for morphisms.
For surjective morphisms, it's okay. For all morphisms.
No. Okay. No, derivations. It's something like map from space itself. It cannot be functorial, but also.
Yes. But somehow.
Some natural constructions.
Yes. So somehow there is a very closely related construction. We can take this TKK of J and we take the universal central extension of it, which then for free Jordan algebras will become a functor. Namely, that's exactly the question that you were asking. We can take, instead of the symbols DAB, so DAB, they are manifestly antisymmetric in A and B, and D of A comma A square is equal to 0 because of the Jordan algebra definition. So we can take this kind of space of universal symbols DAB, the exterior square modular the vector space spanned by all edge A wedge A square. So this has a canonical surjection onto inner derivations. And we can define, so TAG stands for Tits, Allison, and Gao. We can define this thing. We can take, we keep SL2 tensor J, but we replace inner derivations by the space of these symbols.
Actually, it also raises a suspicion. It defines the portion space by some image or some map, yeah? Can one extend to some complex and infinity algebra?
That's a very great question, and I think that an answer of this question might eventually repair the false conjectures that we can talk about in the end. Yes. So somehow, so this is, you modify the TKK construction by saying that now the symbol A wedge B, whenever it acts everywhere as DAB. So just this kind of little silly modification. And it turns out that it's fine, it defines the Lie algebra, and in fact it's the universal central extension of the TKK construction. Now, it turns out that there is a similar thing which works for alternative algebras. So for alternative algebras, there are, you have your own symbols DAB, which are, alternative algebras are no longer commutative, so you have left and right multiplications. And it turns out that if you write this funny formula, the commutator of left multiplications plus the commutator of right multiplications plus the commutator of left multiplication by A and right multiplication by B. Turns out that it's going to be a derivation in the case of any alternative algebra, and actually from the axioms of an alternative algebra it follows that this is antisymmetric in A and B. So it's not written in a way which is manifestly antisymmetric, but it is antisymmetric. Berman and Moody defined a Lie algebra out of any alternative algebra. So you take matrices, 3 by 3 matrices with coefficients in A, with trace 0, you add the inner derivations, and then you more or less play almost the same game as in the Tits-Kantor-Koecher construction, except that the Lie bracket becomes more complicated because there is also, in the case of SL3, SL3 appears in S square of SL3 as a submodule, and so you can, besides, what you should do is something like this. So you cook a commutator out of some natural maps that you have at your disposal. Yes. And then it turns out that there is a similar story of the universal central extension of that construction, namely what is replaced these formal symbols DAB in the alternative case is the following thing. You take the quotient of the exterior square, oh sorry, it should be of A, by the sum of elements like that. So this kind of cyclic sums. So in the case of Jordan algebras, you can also write instead of A wedge A square, if you multilinearize, you can also write something like that. But in the alternative case, the product is no longer commutative. So it's not that sum is not quite obtained from A wedge A square. And then, yes, so you can define this kind of Lie algebra by essentially similar formulas where you replace every time you want to act by the wedge of AB on something, you replace it by DAB. So it's really exactly the same story. And anticipating your question, I can tell you that we here have a story for SL2 and a story for SL3. You might want to ask me what happens for SL4, right? And it turns out that for SL4 there is no longer room for any interesting phenomena. You need to, as coefficients, you can only use just any associative algebra, and so it will be just some. It won't be. So you can get somehow the algebra which is denoted normally SLN of A, so it's where you consider matrices of trace 0, and you also can add the commutator quotient of A times the identity. Yes, right. So now we have these two constructions. We have out of every Jordan algebra, we have a Lie algebra, which is obtained in a natural way, but this kind of functorial construction, and for alternative algebras as well. Okay, so for Lie algebra, you can compute its homology with coefficients, in particular homology with trivial coefficients, which can be defined in many different ways, but the simplest way is to say that we take the exterior algebra of G and define differential by this kind of formula. You take in all possible ways two factors, take their commutator, add up with signs, so it's this Chevalier-Eilenberg formula for homology of Lie algebras. There are many other definitions. We have all sorts of derived functors. You can do it kind of in abelian, non-abelian way, but that should not be our concern now. It will be more of a concern in the context of the question that Maxime asked about Lie infinity extension and so on. Iryna, Kashuba and Olivier Mathieu proposed certain conjecture about free Jordan algebras. So let's note that if we take this construction, Tits-Kantor-Koecher construction, then okay, it has an action of SL2 if SL2 acts on matrices of trace 0 by adjoint representation and by this extra thing as a trivial representation. And in fact, it turns out that if you apply this construction to the free Jordan algebra, it's going to be a free Lie algebra in some sense. If you consider only Lie algebras on which SL2 acts by derivations and all components are just trivial and adjoint, then this is a free object in this category. That motivated the following conjecture, that if you consider this Tits-Kantor-Koecher construction of the free Jordan algebra, you look at the homology. On the homology, SL2 still acts, and the conjecture is that for in homological degrees bigger than 1, the homology has neither trivial nor adjoint component. Of course, if we look at homology in degree 0, it's just a trivial module, and it is easy to show that homology in degree 1 is just a copy of the adjoint module. So, and in some sense, the common sense intuition about free Lie algebras should tell us that this conjecture is obvious, right? Because we know that from classical literature that homology of free Lie algebras is concentrated in degree 0 and 1. Except there is a problem. We're considering free Lie algebras in this funny category, so category of SL2 modules with only trivial and adjoint components. This category is not symmetric monoidal, so we're considering free Lie algebras which are not algebras over the Lie operand. So somehow all the results about homology, they immediately disappear. All intuition that we can rely upon just doesn't exist anymore. So these are very funny Lie algebras. So it's a non-trivial conjecture. It doesn't follow from any general facts. If this conjecture were true, that would be absolutely great because we can compute the Euler characteristics of the Chevalier-Eilenberg complex in two different ways using the complex and the homology, extract multiplicity of the trivial component, multiplicity of the adjoint component, and get all sorts of information about free Jordan algebras, for example. Amazing thing, right? So if the conjecture is true, it has fantastic consequences. Okay, so this is the first of the two conjectures. A guy called Shang in China, he was very inspired by this conjecture and proposed that's analog for free alternative algebras. And you already saw that in the case of the free alternative algebras, we also have a natural Lie algebra construction. So of course we can play the same game. We can say that we compute the homology, and we say that the homology has no trivial and adjoint components in degree bigger than 1. And of course, if this conjecture were true, again, we get a lot of great information about free alternative algebras. So, okay, so now, I first heard of the conjecture of Kashuba and Mathieu, I suppose, back in 2019, and I thought it was absolutely fascinating because generally in the business of Jordan algebras, there are kind of very classical methods going back to 1930s, 1940s, 1950s. There are some new amazing methods invented by Yefim Zelmanov in the 80s, but then somehow there are not so many homological methods, and so if you have some kind of new ideas from Lie algebra homology to work with Jordan algebras, that's fascinating.
It's really interesting this on all questions, these things are graded and in each degree get some funny dimension. Question to study.
Oh, of course, absolutely.
It's a principal computer can.
Yeah, that's exactly, you keep anticipating my slides. Yes, that's exactly what I will be talking about. So somehow let me start with the conjecture of Shang. Yes, so indeed he proved that the prediction of his conjecture for the free alternative algebra is correct for one generator where it's polynomials and one variables, and that is very easy because it's kind of follows from results of Garland and Lipovsky on Lie algebra homology for Katz-Moody, so that is some kind of follows from a known computation. Because the free alternative algebra is algebra of polynomials in one generator is polynomials in one generator. So, and then he only considered elements of degree at most 3 otherwise, so indeed you can check things degree by degree, but well, degree of most 3 is perhaps not enough at all. So I did some computations, and so the first thing I checked that for some small degrees, for degrees at most 6, everything is fine. But then, unfortunately, and this is not a difficult computation, but you already need the computer. Fortunately, there is this program called Albert for computations in non-associative algebras. Also, I have some program for computations of Grosvenor basis in operads that was useful in this business. So somehow, this is something that you definitely can ask the computer to do for you. And then it turns out that for 3 generators, the situation breaks. So somehow the prediction, so you look in degree 7 and you have the predicted dimension 2373, and the actual dimension is a bit bigger by 15. It breaks kind of sufficiently early, so this generalization to the alternative case, perhaps one should say that it's way too naive, because it's, so the correct dimension, again, I double-checked, computed in 2 different ways, looked at the result of Iltikov that I mentioned before, computed using this Albert program. There's absolutely no doubt that this is the correct dimension. So then, so what about the original conjecture about Jordan algebras? So Kashuba and Mathieu checked that for 2 generators, everything is fine in degrees up to 15, so which is already more convincing, perhaps. For 3 generators, they checked for degrees at most 8. And this is already quite significant, because for 3 generators, there are some very particular elements of degree 8 that was discovered by Glenny in 1970s. So as I was telling you, the original motivation of Jordan was about this AB plus BA product, 1/2 AB plus BA in the associative algebras. And then Glenny found that this product satisfies other identities, not just the Jordan identity. And so these Glenny elements, the first non-trivial identities, they are precisely of degree 8 in 3 variables. And so the fact that the conjecture detects existence of those elements, it's a serious argument to suspect that there might be something good to it. So then I did some further computations for 3 generators and checked that the prediction is fine up to degree 12. So, and we actually checked that for any number of generators, things are fine up to degree 10. So, which is already tricky. So to do it for any number of generators, it's enough to consider multilinear elements and look at the SN module structure using the Schur-Weil duality. And somehow for multilinear elements of degree 9 and 10, it's already a heavy computation that was not done before. So this is where somehow so Irvin Hentzel, my co-author, he has been using representations of symmetric groups for dealing with non-associative algebras for many years, and he has insanely efficient programs that can do things. And so for example, the dimensions of these spaces, so the dimension for degree 10 for multilinear elements, it's almost 2 million. So and it's 2 million which is cut out by tens of millions of equations in much bigger spaces. So somehow it's a tricky computation, and without representations of symmetric groups, there is no chance of doing it at least on your computer at home. And just to show you as a fun thing, so this is the not only these, so for multilinear elements of degrees 8, 9, and 10, these are decompositions into irreducible representations of symmetric groups. So for example, this this thing says that the irreducible representation corresponding to the partition 3, 3, 2, 1, 1 appears with multiplicity 226. So it's, and these multiplicities you can also extract from the Kashuba-Mathieu prediction, and yeah, everything is fine up to degree 10. All these numbers match. However, it turns out that already for two generators, the conjecture breaks if you go sufficiently far. The first place where it breaks is degree 19, where it breaks just by 2. So you have 262, 658, 262, 656. Yeah, and this was rechecked in many different ways, so it's not some kind of problem with computer precision and so on. No, it's really this kind of mismatch, which is it is what it is. I guess it suggests that sometimes coincidences go far enough. And then once we realized that, I looked at the alternative case. In the alternative case, it breaks even for two generators in degree 17 or 18. So somehow, and for two generators, the free alternative algebra, as I said, is the free associative algebra. So you have a sequence which up to the 16th term is a power of 2, and then suddenly it's not. Voilà. So let me make one remark. So I was showing you this decomposition into Sn irreducible. So in principle, yeah, so this conjecture predicts multiplicities of irreducibles Sn modules and multilinear elements, or irreducible GLV modules, if you just look at the free algebra itself. And in fact, it turns out that if you look at this carefully, in the case of alternative algebras, this conjecture starts predicting some negative multiplicities starting from some point, starting from degree 10, which is also, of course, a very convincing explanation of why the conjecture of Shang about alternative algebras is false, because multiplicities are non-negative, and it hints about repairing in the L-infinity way. However, for Jordan algebras, all predicted multiplicities that I could compute, well, I went up to degree 25. They're all non-negative. And this is kind of surprising because, so of course, there are some constellations that can, in Euler characteristics, that can produce non-negative numbers, but just the fact that all multiplicities for all partitions are non-negative, maybe it wants to tell us something. So I don't know. It might be something potentially curious. So let me formulate some arising questions. So first of all, the original question remains. So as a result, the two conjectures are false, so we cannot use them to obtain information about free alternative algebras, free Jordan algebras. So if we want to obtain some information, some new ideas are needed, either considering some Lie infinity version of these constructions or doing something entirely different.
Vladimir, do I understand you correctly that these conjectures actually are true for a sufficiently big class? They are not true for infinite sequences of parameters.
No. I mean,
at the bottom they are working.
No. So I mean, the conjecture for alternative algebras. So it only predicts dimensions correctly for the free alternative algebra on one generator. For everything else, it breaks. For free Jordan algebras, same thing. For one generator, okay. For any other number generators, is false. So it predicts dimensions in low degrees, but for each given algebra. But there is no free Jordan algebra except for the trivial polynomial algebra in one generator.
Let me ask you a very stupid maybe question.
Yeah.
So does this conjecture for one generator, when it works,
Yeah.
add anything with respect to previous knowledge?
No, not at all. Absolutely not at all. So the case of one generator was already well known, and it was used as a supporting argument for why the conjecture might be true. Nothing else. So then Kashuba and Mathieu proved a little conditional statement that if their conjecture were true, then this Tits-Kantor-Koecher construction would coincide with the Tits-Kantor-Koecher construction. In other words, the TKK construction of the free Jordan algebra has no central extensions. And this still survives. So, for example, I can prove it for two generators, even though the conjecture itself is false. So maybe at least the TKK algebra has no non-trivial central extensions. Maybe that's one surviving consequence of the conjecture. And similarly, you can ask the same question about central extensions in the alternative case. And again, I can prove it for two generators. So maybe these algebras have no central extensions in general. And then I can ask, of course, maybe this experimental data on sure positivity, that all multiplicities in the Jordan case were non-negative, maybe it persists and maybe it has some smart explanation. So that is still a potentially interesting question. So this more or less finishes the story I wanted to tell you. Since I have still a couple of minutes, I have one more slide with a little unrelated puzzle that I came up with following one of the talks from yesterday. So yesterday, Anastasia was telling us about Motzkin type numbers, which are defined by this recurrence. So as I was saying in the comments after the talk, so there is this strategy of Poincaré where you take, when you have a recurrence like that, you just keep the leading coefficients of the polynomials. So this becomes a very simple guy where just a recurrence with constant coefficients. And Poincaré, so he has some based on this change. So he was explaining that somehow this Mn prime, they kind of, it's approximate, they give some approximations to solutions of the original recurrence. For recurrences with constant coefficients, we know everything, right? So in particular, for this recursion, the characteristic polynomial has the roots 3 and -1. So we should expect that most solutions for the original recursion are asymptotically like 3 to the power n, but there is one exceptional one, which kind of oscillates in some sense around -1 to the power n. So yesterday in the evening, I started playing around. I wanted to find what initial conditions you should take to get this exceptional one. And somehow the computational data predicts a very surprising answer to this question. So that you should take the following initial data. You should take, well, the first you can take something because you can rescale. And the second should be this kind of weird thing made of pi and √3. And so this is somehow, so I computed this number with very high precision, and then there is something which is called inverse equation solver, where you can put number computing with high precision, and it tries to guess what kind of thing it is. And it seems, and so then once I got this guess, I computed 100 more signs after the decimal point, and it still works. So somehow, yeah, so it might be the case that for Motzkin type sequences, this exceptional slowly growing sequence corresponds to this initial data. And if it's true, it would be interesting to see well, where from do you get numbers like that out of the original recurrence? All right, so I'll stop here. Thank you for your patience.
The puzzle.
About the talk, I had a look on the Vladimir article and from 70, and he had a comment which was quite funny. So he, when you gave the sequence of values, he said that he computed them by n up to size n7 general.
Yes.
And then he said that, oh, and we, for those values, we also did a program, we used a program, and he wrote that, oh, it was the proof that the program was correct because the program was getting the same values as us. Mm-hmm. So when nowadays we will more say the converse stuff.
Yes.
And my question is, at some time you said that you or your colleague, you use some powerful algorithm or program to do some computations. Was it in Magma or stuff like this? Or
No. This is completely standalone. So the program that uses representations of symmetric groups to work with identities in non-associative algebras, it's a standalone program that was developed by Irvin Hentzel about 40 years ago and has been he has been improving it ever since. It would be amazing to eventually incorporate it maybe rather into Sage than in Magma to make it freely accessible. And I have been trying to convince, but you know, it is a program which has been always kind of written for personal use, so making it user-friendly, comment and so on. It's a project. So, but in any case, as of now, this is not a part of any standard computer algebra system.
Okay.
So thank you for that algebraic approach. Some time ago I collaborated with Professor Uwe Hogeru. He was interested in the Jordan for Neumann algebra. Mm-hmm. That means you take arbitrary for Neumann algebra because you take matrices, but he take for Neumann algebra, and they anti-commutator, and that was the model for make characterization, like for Neumann divided for Neumann algebra type 1, 2, and 3. Mm-hmm. Also this. So my question is, this was, you know, maybe 20 years ago when I worked with Uwe about some, but my question is, because 3 is algebra, but if you take for Neumann algebra, you have topology, measure theory, because for Neumann is measure theory, non-commutative. So did you know some result in that direction? For Neumann, Jordan free business or something like this. I don't know now what's happening because Uwe died unfortunately 10 years ago. Mm-hmm. But what do you know? Maybe you can sign direction or say something.
Yes, that's right. So when you start considering topological algebras, when things become more tricky and the circle of questions I've been discussing doesn't have direct connection to this, except for the fact that why do we care about free algebras? Because somehow if you have some expression involving 5 elements in the topological algebra, that expression you might want to express in some kind of standard form. So it's a question about choosing a good basis in the free algebra. That's kind of the motivation. Yeah.
And then you have some example that for Neumann.
No. So the takeaway from my talk is that these beautiful conjectures are unfortunately false, and so they don't bring new information about normal forms and bases and dimensions in free algebras. So everything is still wide open.
Thank you very much.
Okay. No more questions. Thanks, speaker again, and resume in 5 minutes.